Hello guys, welcome to our Excuse Me Max channel. This is part 3 video, continuation of part 2 in which the problems between 0 to 2 pi were discussed. Now coming to the next problem in the interval 0 to 2 pi, we have expand f of x is equal to x sin x in the interval 0 to 2 pi as a Fourier series. Now coming to the solution, here the function is x sin x between the interval 0 to 2 pi. You know the function f of x is equal to a naught by 2 plus summation n from 1 to infinity a n cos nx plus b n sin nx. So by Euler's formula you have to find out a naught, a n and b n here. First let us find out a naught, which is equal to 1 by pi integral 0 to 2 pi f of x dx. Substituting the function x sin x in place of f of x and integrate with respect to x. Using integral uv dx formula, we integrate the function x sin x, keeping u is equal to x and v is equal to sin x. Here differentiation is denoted in red color and integration is denoted in green color. Substituting the upper limit in red color, we get 2 pi into minus 1 since cos 2 pi is equal to 1 and sin 2 pi is equal to 0. And by applying the lower limit in green color, the whole term will get 0 since substituting x is equal to 0 and sin 0 is equal to 0. Therefore, our a naught is equal to minus 2. Next to find an is equal to 1 by pi integral 0 to 2 pi f of x cos nx dx. Substitute the given function in place of f of x and integrate. We get 1 by pi integral of x sin cos nx, which is like cos a sin b. We have 4 trigonometric formulas which are given here. We can take either 2 sin a cos b or 2 cos a sin b. Here for our convenience, we take the second one, 2 cos a sin b formula. That is cos a sin b is equal to sin a plus b minus sin a minus b the whole divided by 2. We replace our integral as 1 by pi integral of x cos nx sin x, which is like x into cos a sin b. We apply the formula cos a sin b here, taking cos nx as cos a and sin x as sin b. You can also take sin a cos b also, both are correct. By applying cos a sin b formula, we have 1 by 2 pi integral 0 to 2 pi x into sin n plus 1 into x minus sin n minus 1 into x dx. Divide by 2 will come outside as 1 by 2 pi. Now integrating using Bernoulli's formula, taking u is equal to x and v is equal to sin n plus 1 into x minus sin n minus 1 into x. Here differentiation is given in red color and integration is given in green color. Now after substituting the values in Bernoulli's formula, apply the upper limit 2 pi, which is in red color. Since we have cos 2n plus 1 into pi is equal to 1 and cos 2n minus 1 into pi is equal to 1 and sin 2n plus 1 into pi is equal to 0 and sin 2n minus 1 into pi is equal to 0 and cos 0 is equal to 1, sin 0 is equal to 0. So with these values, we get 1 by 2 pi into 2 pi minus 1 by n plus 1 plus 1 by n minus 1. This 2 pi will get cancelled. So finally we get minus 1 by n plus 1 plus 1 by n minus 1 with the upper limit. Next, applying lower limit 0, we get first term 0 as x is equal to 0 and second term also 0 since sin 0 is equal to 0. So therefore our lower limit is equal to 0. So our an is equal to minus 1 by n plus 1 plus 1 by n minus 1. We know that n square minus 1 is equal to n plus 1 into n minus 1. Using this formula, we get an is equal to 2 by n square minus 1 when n not equal to 1. Now find out the value of an when n is equal to 1. Put n is equal to 1 in an. We have a1 is equal to 1 by pi integral 0 to 2 pi x into 2 cos x sin x dx. Since you have the formula sin 2x is equal to 2 sin x cos x, from this sin x cos x is equal to sin 2x divided by 2. That is, a1 will become, taking 2 outside, we get a1 is equal to 1 by 2 pi integral 0 to 2 pi x into sin 2x dx. Now integrate using Bernoulli's formula, we get Therefore a1 is equal to 1 by 2 pi into x into minus cos 2x by 2 minus 1 into minus sin 2x by 4 with the limit 0 to 2 pi. Differentiation is given in red color and integration is given in green color. Now apply the upper limit 2 pi. In first term we get 2 pi into minus 1 by 2. Since cos 2 into 2 pi, that is cos 4 pi is equal to 1, minus 0 since sin 4 pi is equal to 0. Now apply the lower limit, you get 0 as x is equal to 0 in the first term and 0 in the second term as sin 0 is equal to 0. Therefore a1 is equal to 1 by 2 pi into 2 pi into minus 1 by 2. 2 pi will get cancelled. Therefore a1 is equal to minus 1 by 2. Now to find bn. Bn is equal to 1 by pi integral 0 to 2 pi f of x sin nx dx. Substitute the given function in place of f of x. We have 1 by pi integral 0 to 2 pi x into sin nx sin x dx. Now it is like sin a sin b. Apply 2 sin a sin b formula here. We get, taking 1 by 2 outside, we get 1 by 2 pi integral 0 to 2 pi x into cos n minus 1 into x minus cos n plus 1 into x dx. Integrating using Bernoulli's formula, we get, by differentiating u is equal to x with respect to x and integrating v with respect to x. As usual, differentiation is given in red color and integration is in green color. The values are given as bn with the limits 0 to 2 pi here. Now apply the upper limit 2 pi in place of x in bn. We get 1 by n minus 1 the whole square minus 1 by n plus 1 the whole square. Because in first term sin 2n minus 1 into pi is equal to 0, sin 2 into n plus 1 into pi is equal to 0. So 0 into 2 pi is equal to 0. Then minus and minus will become plus and cos 2 into n minus 1 into pi is equal to 1. Cos 2 into n plus 1 into pi is equal to 1, which gives 1 by n minus 1 the whole square minus 1 by n plus 1 the whole square. Now applying the lower limit, which is denoted in green color, we get first term as x is equal to 0 and also sin 0 is equal to 0. Then minus and minus becomes plus, and since cos 0 is equal to 1, we get second term as 1 by n minus 1 the whole square plus 1 by n plus 1 the whole square. So finally all the terms will get cancelled. We get bn is equal to 0 when n not equal to 1. Now find out the value when n is equal to 1 here. Put n is equal to 1 in bn. We get b1 is equal to 1 by pi integral 0 to 2 pi x sin square x dx. We know the formula sin square theta is equal to 1 minus cos 2 theta the whole divided by 2. Now take 1 by 2 outside, then it becomes 1 by 2 pi integral 0 to 2 pi x into 1 minus cos 2x dx. Now integrate keeping this as uv using Bernoulli's formula. We have b1 is equal to 1 by 2 pi into x minus sin 2x by 2 minus 1 into x square by 2 plus cos 2x by 4 between the limits 0 to 2 pi. Here differentiation is given in red color and integration is given in green color. Now apply the upper limit 2 pi, which is in red color, in place of x. We get 2 pi into 2 pi minus 0 minus 4 pi square by 2 minus 1 by 4. Since sin 2 into 2 pi, that is sin 4 pi is equal to 0 and cos 2 into 2 pi, that is cos 4 pi is equal to 1. Now apply the lower limit 0, which is in green color in b1. We get 1 by 4. Since first term becomes 0 as we substitute 0 in place of x, and in second term it becomes 0 plus 1 by 4 since cos 0 is equal to 1. So therefore by simplifying the values we get b1 is equal to pi. Now we have 4 values a0, an, a1, bn and b1. So our f of x can be written as f of x is equal to a0 by 2 plus a1 cos x plus b1 sin x plus summation n from 2 to infinity an cos nx plus summation n from 2 to infinity bn sin nx. By substituting all the 4 values we get f of x is equal to minus 1 minus 1 by 2 cos x plus pi into sin x plus summation n from 2 to infinity 2 by n square minus 1 cos nx. So therefore by expanding the summation we have f of x is equal to minus 1 plus pi into sin x minus 1 by 2 cos x plus 2 by 2 square minus 1 cos 2x plus 2 by 3 square minus 1 cos 3x plus etc., which is the Fourier series of our function. Next problem, determine the Fourier series for the function f of x is equal to x into 2 pi minus x of period 2 pi, that is 0 to 2 pi, and hence deduce that pi square by 8 is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. Solution of this problem is, we know that the Fourier series of f of x of period 2 pi is given by f of x is equal to a naught by 2 plus summation n from 1 to infinity a n cos nx plus summation n from 1 to infinity b n sin nx. By Euler's formula, we have to find out a naught, a n and b n. First, to find a naught. Our a naught is equal to 1 by pi integral 0 to 2 pi f of x dx. Put the given function in place of f of x and integrate. We have 1 by pi integral 0 to 2 pi x into 2 pi minus x into dx. Multiply x inside, you get 1 by pi integral 0 to 2 pi x minus x square into dx. Now integrating with respect to x, we get 1 by pi into pi x square minus x cube by 3 between the limits 0 to 2 pi. Applying the limits and after simplifying we get a naught is equal to 4 pi square by 3. Next to find an. An is equal to 1 by pi integral 0 to 2 pi f of x cos nx dx. Substitute the given function in place of f of x, we get 1 by pi integral 0 to 2 pi x minus x square into cos nx dx. Take u is equal to 2 pi x minus x square and v is equal to cos nx. And integrate using Bernoulli's formula with respect to x, we have u, u dash, u double dash etc. and v1, v2, v3 etc. Differentiation is given in red color and integration is given in green color. We have an is equal to 1 by pi into 2 pi x minus x square into sin nx by n minus 2 pi minus 2x into minus cos nx by n square plus of minus 2 into minus sin nx by n cube with the limits 0 to 2 pi. Now apply the upper limit 2 pi which is in red color. First term becomes 0 as sin 2n pi is equal to 0. Second term becomes 2 pi minus 4 pi into 1 by n square. Since cos 2n pi is equal to 1 and minus will become plus there. And the third term will become 0 as sin 2n pi is equal to 0. Now apply the lower limit which is in green color. First term becomes 0 as sin 0 is equal to 0. Second term becomes 2 pi into 1 by n square since cos 0 is equal to 1. And the third term becomes 0 as sin 0 is equal to 0. Now after simplifying the values, we get an is equal to minus 4 by n square. Next to find bn. We have bn is equal to 1 by pi integral 0 to 2 pi f of x into sin nx dx. Substitute the given function in place of f of x and integrate using Bernoulli's formula. We have bn is equal to 1 by pi integral 0 to 2 pi x minus x square into sin nx dx. Take u is equal to 2 pi x minus x square and v is equal to sin nx. Here differentiation of u is given in red color and integration of v is given in green color. That is, after integrating, our bn is equal to 1 by pi into 2 pi x minus x square into minus cos nx by n minus 2 pi minus 2x into minus sin nx by n square plus into minus 2 of cos nx by n cube with the limit 0 to 2 pi. Now substitute the upper limit 2 pi in place of x. We get first term as 0 since 2 pi x minus x square is equal to 0 as x is equal to 2 pi. And second term is equal to 0 as sin 2n pi is equal to 0. And third term is equal to minus 2 by n cube since cos 2n pi is equal to 1. Now apply the lower limit 0 in place of x which is denoted in green color. We get first term as 0 since 2 pi x minus x square is equal to 0 at x is equal to 0. and second term is equal to 0 since sin 0 is equal to 0. And third term is equal to minus 2 by n cube since cos 0 is equal to 1. After simplifying we get Bn is equal to 0. Therefore our a0 is equal to 4 pi square by 3, an is equal to minus 4 by n square and Bn is equal to 0. Therefore our Fourier series f of x is given by f of x is equal to a0 by 2 plus summation n from 1 to infinity an cos nx plus summation n from 1 to infinity bn sin nx. Substituting the values of a0, an and bn and simplifying we get f of x is equal to 2 pi square by 3 minus 4 into summation n from 1 to infinity cos nx by n square. Expanding the summation we get f of x is equal to 2 pi square by 3 minus 4 into cos x by 1 square plus cos 2x by 2 square plus cos 3x by 3 square plus etc. is the required Fourier series of the given function. Keep this Fourier series as equation number 1. Now coming to the deduction part of the problem. In our problem, you are asked to deduce the series as pi square by 8 is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. To deduce the series, we assume a point at which the given function is continuous at that point. We have discussed the continuous function in the previous part 2 video. Before watching this deduction part, have a look on part 2 video so that to understand easily. And also we have discussed some shortcut to assume the point A. Here, our Fourier series is in cosine function. We assume 0 or pi to deduce the series. Here in this problem, we assume both 0 and pi to deduce the given series. So at first, we put x is equal to 0 in equation number 1. So our equation 1 becomes, by putting x is equal to 0, we have 0 on left hand side since the given function 2 pi x minus x square is equal to 0 at x is equal to 0. And on right hand side, we have 2 pi square by 3 minus 4 into 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. as cos 0 is equal to 1. Simplifying further by taking 2 pi square by 3 on left hand side, we get pi square by 6 is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus etc. Put this as an equation number 2. Again put x is equal to pi in equation number 1. We have our f of x is equal to pi square. That is pi square is equal to 2 pi square by 3 minus 4 into 1 by 1 square into cos pi plus 1 by 2 square into cos 2 pi plus 1 by 3 square into cos 3 pi plus etc. Taking 2 pi square by 3 and 4 on left hand side and substituting the values of cos pi, cos 2 pi, cos 3 pi etc. in which the values are minus 1 plus 1 minus 1 etc. and simplifying we get pi square by 12 is equal to 1 by 1 square minus 1 by 2 square plus 1 by 3 square minus etc. Keep this equation number 3. Now adding equation 2 and equation 3, we get pi square by 4 is equal to 2 into 1 by 1 square plus 1 by 3 square plus etc. Since plus 1 by 2 square minus 1 by 2 square, similarly plus 1 by 4 square minus 1 by 4 square etc. will get cancelled. Finally, we get pi square by 8 is equal to 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus etc. Hence proved the solution. Hi guys, so far we have solved 4 important university problems under 0 to 2 pi interval in various different functions in combining part 2 and part 3 videos. In next part 4 video, we can see some important university problems as an assignment for practice. If you like this video, share and subscribe the channel. Thank you.